Listed here are some common properties of logarithms. A through D are pretty basic. Understanding, remember, a logarithm is just an exponent. So when you prose these logarithms in terms of the exponent, like A, what exponent on A gives you a value of 1? Of course, it's 0. Or what exponent on A gives you back A? Only 1 is the correct exponent. A to the 1 is A, and A to the 0 is 1, so not surprising. Even this log base A of A to the x, what exponent on A gives you A to the x? Well, obviously A to the x, so there is that. Now we have the same inverse thing kind of in reverse here. A to the log base A of x is just x, so you could say that the exponent and the logarithm undo each other. They're gone, and we're just left with the x, right? These guys are gone, and we're just left with the x's. Now E is what we call the one-to-one property. So if we take the log of x and the log of y, they must of course equal each other as long as they have the same base, not surprising. And then the last three are the rules of operating with logarithms. The first one is that if you have a product in an argument, that's the sum of the separate logarithms. The quotient becomes the difference. And if you have an exponent, n, that exponent can simply be a constant multiplier. Now remember, these things are exponents, so they behave like exponents. If you have a to the x times a to the y, what we do with those exponents is simply add them together for the base. And the same thing for the log. Log of u times v is what a power on a makes u times v. That should be the power on a that makes u plus the power on a that makes v. So these guys are the rules. They're the only rules for messing with logarithms, so don't invent any. Most importantly, remember that logarithms do not distribute. Students like to cook up this rule because distribution is handy, and sometimes they think it makes their life easier. So they'll say, you know what, if I have the log base a of u plus v, I should just call that the log base a of u plus the log base a of v, because why can't I just distribute the log? I might as well. Sounds good to me. I open up that argument, but it is not true. So do not do that. Those are not the same case, because when we have by the properties of logarithms, the real rules, when you're adding two logarithms together, this is really the log base a of the product u times v. So be careful there. Let me see if I can't move this stuff over. It's not distribution. The addition makes it log of the product. Okay, so let's use those things to simplify some stuff with numbers and then see if we can't solve some equations. So log base 9 of 27 is the same thing as log base 9 of 3 times 9, right? 3 times 9 makes 27, so if I change that up, then this is log base 9 of 3 plus, because they're multiplied together, the log base 9 of 9. Well, log base 9 of 9 is just 1, right? 9 raised to the power 1 makes 9, so we can simplify that piece up. And simplify 9 to log base 9 of 9 is 1, and log base 9 of 3, let's think of that 3 as log base 9 of 9 to the 1/2, right? Because the square root of 9 is 3. Plus this 1, so log base 9 to the 1, log base 9 of 9 to the 1/2, those log base 9 and the exponential and 9 kind of cancel, they undo each other, so that term is just 1/2. That leaves us with 1/2 plus 1, or 3/2. That's how we can simplify with numbers. What we want to do really is simplify with equations or variables and solve for an unknown. In the quest for this solving equation skills or tactic, we first have to be very good at manipulating the logarithms in terms of these logarithm properties. So this first question asks us to expand the expression That means we're going to use the rules to stretch out this logarithm as much as we can. First thing you'll remember is that every time we have multiply, that turns into an addition, and then the powers can come down. So if I expand over that multiplication, this becomes log base a of x squared plus log base a of the cube root of 5 plus x squared. Well, x squared, that's an exponent, so the 2 can come down. That's the power property of logarithms. This is equal to twice the log base a of x. Plus, and how can we think about this cube root? Well, instead of cube root, let's rewrite it as this stuff to the 1/3 power. That's the same thing, but now it's written as an exponent, which also can get demoted. So if we pull down the 1/3, we have 1/3 log base a of 5 plus x squared. And then we're stuck. We expanded the logarithm as much as we can, and we have written the sum of the logarithms, and we have multiples instead of power. So that's as expanded as it can get. To do this one again, we have the natural log of a quotient all raised to the 5th power. So we're just like unwrapping this logarithm present. So just like with a gift, you have to get the outer layers off first, and right now the outermost layer is that 5. So let's bring down the exponent of 5. That makes it 5 times the natural log of x minus 5 cubed over the square root of x. So the next biggest layer is this division. So let's open it up over the division, or over the quotient. That's 5 times the natural log, divide becomes subtract, x minus 5 cubed minus the natural log of x. The square root of x is x to the 1/2. And now that we've opened up that division, the next natural layer is to bring down these exponents, which can get unpacked, the powers can. So that's 5 times 3 natural logs of x minus 5 minus 1/2 natural log of x. And we can get rid of those brackets by distributing the 5. 5 times 3 is 8 times the natural log of x minus 5 minus 5 times 1/2, 5/2, and the natural log of x. So we've taken a big complex logarithm and expanded it into 2 simpler logarithms. We do this in calculus before we take a derivative. It's easier to differentiate this than it is to differentiate that by a long stretch. So these are good skills to cultivate. And going the opposite direction, which we'll explain a little more in this class, when you want to condense the expression, like shove all those logarithms together into a single logarithm, so we can mess with the argument or break free from that logarithm. So just like the present, we had to unwrap the outer layers first. Now we're packing that thing back up. So we need to move the powers up first before we can combine them by the plus to product and subtraction to quotient properties. So this is now the natural log of u to the 5th plus the natural log of v to the 6th minus the natural log of w to the 3rd. And then we can combine them. Remember, addition means multiplication, so these 2 logs combine into one single logarithm of u to the 5th times v to the 6th, that's the argument, minus the natural log of w cubed. And the subtraction becomes division when we shove these logs together, so they condense, they simplify into a single logarithm, u to the 5th v to the 6th over w cubed. So there, now we have collapsed or condensed into a single logarithm. Example B gets even bigger. Let's see what we have here. To do this one, we're just going to take it one step at a time. It might seem a little overwhelming at first, but I'm sure we can handle it. So first, before we can combine anything by plus and minus, we have to get these constants out of the way, pack them up. So we have a 1/3 constant and a 2 constant, meaning this expression now becomes log base a of x plus 3 to the 1/3 minus log base a of x plus log base a of x minus 1 squared. So now the constants are out of the way. We can shove the logarithms together. Once you practice this enough, you can come to realize that negative stuff goes in the denominator, that's a division operator, and positive stuff goes in the numerator of the argument. Because we're adding those two together, it's the same thing as multiply. So all these three log base a's combine into a single log base a. The numerator are those positive terms, x plus 3 to the 1/3 times x minus 1 squared, divided by the dude who had a negative coefficient x. That's the part of the quotient. So you could have done that in 2 steps as we did in the previous example, or once you have plenty of practice, you might as well just do it in 1 step, which is the most efficient. Now our job, the whole reason we do anything in algebra, is to solve for x. So here are some strategies for solving for x when x is wrapped up in some exponential or logarithmic business. We need to break it free. We have these things on the left called the one-to-one properties. So if we have an exponent equals an exponent or a log equals a log, then we can simply expose what those arguments are. The exponent must be the exponent, or the argument must be the argument. Those things have to be equal. Or we use the inverse property of exponents and logarithms to get rid of the thing we have. So think about this as like, if you had that y equals x minus 4 and you want to solve for x, you would do the inverse of minus 4. You would add 4 to both sides. Similarly, if we have that y equals 5 to the x, but we need to know what x is, we need to undo that exponent. Undo 5 to the x would be to take the log base 5 of both sides. So log base 5 of y equals x. That undoes the exponential. We converted it. So we have plenty of examples there, but first let's get a strategy. The first thing is we'd like to use the one-to-one property if possible. We can use one-to-one if we have the same base or the same log and they equal each other on each side of the equation. Then they can be the one-to-one property. If that doesn't happen, then we want to isolate a single logarithm or an exponential, just that one piece, and convert it from a log or an exponential to the other form, do the inverse to break free. And if that doesn't work, then we might have to use the inverse relationship on both sides. Maybe we like take the logarithm of both sides or raise both sides to the same power so that we can bust out, right? Get the variable out of that function. Now, anytime we do logarithms, we have to check the solutions because the domain of the logs does not include negative numbers. So let's see what some of these look like. Here we have an example. We have 1/5 raised to the 3x equals 125 to the 1 minus x. So if we could shove this thing into looking like 5 to the x equals 5 to the something else, then we could use the one-to-one property where those exponents must be the same. That would be the easiest way to solve that. Not the only way, but the most direct. So let's mess with 1 over 5. And see if we can't turn it into 5 to some power. For example, 1 over 5 is 5 to the minus 1, right? 5 to the minus 1 to the 3x equals, what's 125 as an exponent of 5? 125 is 5 cubed to the 1 minus x. So now they both have a base of 5. We just need to clean up the exponents. 5 to the minus 3x equals 5 to the 3 minus 3x. Because we used powers of powers and multiplied to combine the exponents. So now they're both exponents on 5, and we care about where negative 3x equals 3 minus 3x. So what are those solutions? Well, let's add 3x to both sides. That yields 0 equals 3. Is that true? Ever? Nah, that is not true. That's a false statement. If it's not true, 0 is not equal to 3. That means that this equation has no solution. Disappointing, but true. Let's look at another one. So what about this one? 3 log base 4 of x equals log base 4 of 5. Well, we have two parts that are the same log base 4. And if we have log base 4 equals log base 4, we could set the arguments equal. We just have to get rid of this 3. So let's pack it up and make this log base 4 of x cubed equals log base 4 of 54. Now we can effectively remove the log from both sides. X cubed must equal 54. We have the same expression on both sides, so the arguments must be the same. If x cubed is 54, x is none other than the cube root of 54, which simplifies to 54, I think is divisible by 27. Cube root of 27 times 2, right? 27 times 2 makes 14, yeah. And the cube root of 27 is 3, so it's 3 cube roots of 2 for a solution. Now the plot thickens. There's more than one logarithm involved, and so what we cannot do is just say that these arguments, 3x, 5x, and x plus 1, all equal each other. Like, we can't just drop the logs, because they do mean something. So before we can peel them off or get rid of them, we need to have log equals log. We need natural log of something equals natural log of something else in order to get rid of the logarithms. So over here on the right hand side, we could shove those two logarithms together. This is the natural log of 3 times x on the left equals the natural log of 5x upstairs over x plus 1, because by those properties of logarithms we can combine them as a quotient. And now that we have log equals log, we see that 3x equals 5x over x plus 1. We can drop the log, we can just mess with the arguments. Now we have to solve this, so maybe think of this as 3x over 1 and cross multiply, or perhaps you just multiply both sides by x plus 1. 3x times x plus 1 equals 5x, so 3x squared plus 3x equals 5x, and we need to solve for x, so let's subtract 5x, 3x squared minus 2x equals 0. Uh, 3x minus 2x, factor out the x, 3x minus 2 equals 0, so x should be 0 or 2/3. But because these are logarithms, we need to go back and check. Just to make sure. Sometimes answers show up which actually aren't answers, and that's a problem for us, so let's check it. One solution we got was 0. We just want to make sure that that's valid. The natural log of 3 times 0 equals the natural log of 5 times 0 minus the natural log of 0 plus 1. The only one we could evaluate there is the natural log of 1, because the natural log of 0 is undefined or doesn't work. If you don't trust me, put it in your calculator. This is a problem. That's an error. It's an inappropriate solution. Thanks for showing up, but we don't actually need you 0. Let's try 2/3. Just to make sure it's legit. So the natural log of 3 times 2/3 equals the natural log of 5 times 2/3 minus the natural log of 2/3 plus 1. That's the natural log of 2 equals the natural log of 10/3 minus the natural log of 5/3. Those are all valid numbers. If you want to, you can combine them and simplify, make sure that it actually does work out. You could just get the decimal approximations in your calculator, both sides, to check it out. But we don't have to throw out 2/3 because it was not outside of the domain of the logarithm, so we have one valid solution. Example E requires that we peel off this logarithm. We want to undo the log so we can get out, because there's not a log on each side that we could set the arguments equal to. They're not exponents. So in order to get out of the logarithm, what we want to do is convert it to an exponential expression. That's why we practice this so much at the beginning of the module. Remember that if y equals log base a of x, that's the same exact thing as saying that a to the y equals x. So let's use that thing, that conversion principle. It's a two-way street to get out of the logarithm. The base is x. X to the power 3 equals the value 64. So now we can solve for x. X is the cube root of 64, also known as 4. So by converting to exponential or getting out of the logarithmic form, we have a solution that works. Log base 4 of 64 truly is 3. The next level of difficulty occurs when we have logarithms, but not every term has a logarithm on it. So this -1 is not going to allow us to make a log equal log and just mess with the arguments. What we need to do is have all the logs on one side and all the numbers on the other. So let's move the log base 6 over and the -1 to the other side. So essentially we'll add 1 to both sides and subtract log base 6 of x minus 2 from both sides. So that's kind of crawling there, but just keep track of everything. Or maybe you think of it as log base 6 goes over and then the -1 goes to the other side. The result is this: log base 6 of x minus 1 minus log base 6 of x minus 2, they don't have the same arguments, so we can't combine them, they're not like terms, equals positive 1. Now on the left-hand side we can shove those logarithms together, so log base 6 of x minus 1 over x minus 2 because of division equals 1. And now we have a log expression, log base 6 of something equals 1, with that we can escape, we can get out of this if we convert it to exponential. Converting to exponential means we take the base is 6, raise that to power 1 equals the argument, x minus 1 over x minus 2. Alternatively, one other way that I've seen students discuss this, and when that convert to exponential step kind of escapes them, the other way to do it is just take this guy, which is the base, and raise both sides to be a power of that base. So if we have 6 to the log base 6 equals 6 to the 1, then the 6 and the log base 6 go away. You have x minus 1 over x minus 2 equals 6 to the 1, which is just 6, right? So this is the same result as you can see in blue or green. Either you convert it to exponential using that property, or in green you raise both sides as an exponent, or make both sides, let's say. Of the base, whatever the base is that's given, sometimes 6, sometimes z, maybe 10, who knows, and then solve from there. So we have 6 equals x minus 1 over x minus 2, multiply both sides by x minus 2, 6 times x minus 2 equals x minus 1, which means that 6x minus 12 equals x minus 1, so 5x equals 11, so x equals 11/5. Alright, so the very last example that we'll do in this video is solve this one. Again, there's only one instance of a logarithm, so we start to thinking that the only way we can get out is convert to exponential, but before we do that we need to isolate the logarithm. So let's add the log to the other side. So both of these terms are positive. 22 equals the natural log of 2 minus x. Now to get out of the logarithm you have two choices: convert to exponential or we can raise both sides as a power, make both sides a power of the base of this log, which is e. Either way, the result from this would be e to the 22 equals 2 minus x, either one of those methods. So now we just want to solve for x. X equals Now we'll add x to both sides and subtract e2 minus e to the 22. Kind of maybe scary because it looks funny, but that's the solution. It's a number. You could get a decimal place and approximate if you need be.